So are you ready? Okay. So then let's get started. So today we are very happy to have Yuki Koto from Academia Sinica. So he will talk about quantum cohomology of toric bundles. Yeah, please.
I want to explain quantum cohomology. Explain demonstration and reduction.
Sorry, maybe you need to wear a microphone. So it's over there.
Okay. Okay. Let B be a smooth projective variety and take vector bundle over B. The typical toric bundle typical example is projectivization of vector bundle. This gives P R minus one bundle over B. And its usual cohomology is well understood. It can be described using cohomology of base space and using a characteristic class of vector bundle. Like this. A quantum cohomology is by definition deformation of usual cohomology. Here we use genus zero Gromov-Witten theory for total space. Anyway, we have deformation of usual cohomology. Now, as explained, cohomology of total space can be understood by cohomology of base space and cohomology of fiber and its growing data. There is a natural question. How about quantum cohomology? So if we know quantum cohomology of base space and quantum cohomology of fiber, and growing data, then can we compute quantum cohomology of total space? Yeah, more generally, for any fiber bundle, we can consider the same question. Here we replace by F, and here a total space. Can I?
It's already the highest.
Oh, okay. I think this is not a good idea to write. Is it okay?
Yeah, I still prefer. Or you could also use one blackboard if you go.
Only one blackboard.
So you
Okay.
yeah.
Okay, I use only this blackboard. Okay. The quantum cohomology can be studied by I function. I will explain later. I function is some kind of generating function of Gromov-Witten invariant. The main result is yeah, I give an explicit formula. This is called mirror theorem. So I prove mirror theorem for toric bundles. Okay. Gromov-Witten theory, Gromov-Witten invariance defined as virtual counting of curves on some variety. And there are infinitely many invariants for one projective variety. And by using Gromov-Witten invariants, we define quantum cohomology. As I said, quantum cohomology is this set, and this already are endowed with a ring structure induced by ring structure of usual cohomology, but we define another ring structure on here. Star denote quantum product. here, fx is a cone of generated by effective curves. And tau denotes a parameter for cohomology. So here phi one, phi zero, phi one, phi two. These are basis of usual cohomology. These are C bases. So roughly speaking, tau corresponds to a parameter of deformation of cohomology. Cohomology has canonical pairing defined by integration. This defines non-degenerate pairing on cohomology. For alpha, beta, gamma in quantum cohomology, alpha star beta is defined by this formula. Q of D denotes the element of monoid ring. Sorry, I forget to explain this notation. For ring, since this is a monoid, we can consider a monoid ring. So for D, the element of this ring is written as a finite sum of such terms. This is a formal variable. And since effective fx is strictly convex, we can take its completion. Canonically, we can take its completion. So this is infinite sum in general. Like this. This is Gromov-Witten variance. Degree D Gromov with the invariance. This is roughly speaking, this is counting of rational curves. I'll explain using the example, okay? Yeah, I will give example later. Anyway, this is a definition of quantum cohomology and quantum product. Note that this pairing is non-degenerate, so by this formula, alpha star beta is determined. And by definition, the leading term is this. So D set D equals 0 and N equals 0. Then yeah, we should consider this term. This is by definition just integration of their cup product. So this is a usual cup product with taking pairing with gamma. So alpha star beta equal alpha cup beta plus some higher terms. So we can see quantum cohomology as deformation of usual cohomology. Okay. Is there any question? Okay. And quantum cohomology of projective space is if we set tau equals 0. So if we ignore these parts, then yeah, quantum cohomology can be written explicitly. On taking the limit we obtain this ring. You know, this is a usual cohomology of projective space.
So if we only want to consider some deformation of the cohomology ring, can we simply set as you do here tau to be 0? So is it something interesting or I don't know?
You ask why I
No, I'm asking. So for arbitrary x,
Yeah.
for arbitrary x. So if we consider just QH of x,
Yeah.
but with tau equals 0,
yes.
is this ring
Yeah. It is also a famous object. This is actually called small quantum cohomology. So yeah, tau is a parameter for total cohomology, right?
Mm.
But Q corresponds remember that D is an element of Fx, and this is second homology class. So Q corresponds to second cohomology. So actually, we can deform cohomology to arbitrary direction in total cohomology, but this corresponds to, we only consider the direction of H2. Yeah. It is called small QH. For fun variety, maybe many people want to understand small quantum cohomology for fun varieties. Okay. Yeah, I want to check this relation in the simple case. One comment. If we understand small quantum cohomology, then in this case, actually we can compute total quantum, how to say? Yeah, actually, I like here the definition of quantum cohomology. And this is called big quantum cohomology. Yeah. In this case, or more generally, if H star is generated by H2 as a ring, then if we know small quantum cohomology, we can compute a big quantum cohomology. Anyway, I go to case. We should prove that we should check this relation. Yeah, also we should check other relations. But these are easy. The most difficult part is this. So P is class corresponds to line. Yeah, more precisely, P is first Chern class of anti-tautological line bundle. By taking Poincare dual, that corresponds to P2 line and point. And Okay, by definition, this pairing can be described as as this. Here, effective curve class, effective cone can be identified with non-negative integers in R82. So we should compute these terms. So on the other hand, by using this relation, this pairing should be equal to 0 for I equal 0, 1, and Q for I equal 2, okay? Because for I equal 2 case, here we can consider, we replace this product by Q. Mm. This is by definition just an integration of cup product. So this equals 0. And for d equal 1, we first take Poincare duals. And put them on P2 in a general place. And then consider rational curve of degree 1. So take some line and we put some condition on she. She is line and this intersects with these three sub-varieties. But P2 automatically intersect. So she should intersect with L and point. And we consider a mark point on C, 3 mark point. And for each mark point, for the first marked point, C intersect with the first subvariety. So we should put first mark here. On second mark, we put here. And for third mark, we can put it arbitrary point. But the dimension of this set is 2 because yeah, she should pass through this point. So such a line, the dimension of such a line is 1. Yeah, and any line intersect with another line. We can put first marked point and second marked point uniquely. But we should choose which point we put third marking. So we choose which line and where we put third mark point. So dimension is 2. Here we use convention that the number of sets equals 0 if this is a dimension over than 0. This is not a finite set. So this is 0. D equals 0 is the same. This is just an integration. For D equal 1, we take their Bankai duals and put on P to them. Like this. And counting lines. Sorry, just counting lines that intersect with these 3 subvarieties. And we should put marking on each intersection point. And this set is dimension 1. So this is also equal to 0. And finally, y equal 2 and d equal 1. Poinkai draws one line and 2 points. So we take one line and 2 points and counting curves passing through these 3 subvarieties. Then this is uniquely determined. Marking is also uniquely determined by the condition that first marking point should put on the first subvariety. So this is 1. So we obtain this formula. Okay. Is there any question? In projective space case, it is, for P2 case, it is not so hard to count such curves. But if we consider a big quantum cohomology, we should deal with more difficult problem, counting degree D curves passing through 3D -1 point. It is very difficult to write down its solution. And more generally, for general projective variety X, Gromov-Witten invariants don't coincide with actual counting. In this case, Gromov-Witten invariants coincide with actual counting. But in general, it is just virtual counting. This is actually defined by integration or intersection theory over moduli space. So it is hard to compute directly. So we should use other method. Yeah, I want to introduce so-called Giventhal formalism. Quantum cohomology is it is known that quantum cohomology is closely related to generating function Gromov-Witten invariants. Giventhal interpret this relation by geometric interpretation. Space. He introduces this space. This is called Giventhal space. Here, omega denotes symplectic form defined by this pairing. This actually defines symplectic form on this carry HX. And by using Gromov-Witten invariants, he construct Lagrangian subspace. And this is called Lagrangian cone. The elements of Lx is some kind of generating functions. I omit the detailed explanation. Generating function of Gromov-Witten invariants of X.
So the pair, so omega you defined. So is it the power series in Q?
Power series.
Of course.
Yeah, this is the same as this.
Yes. So the pairing omega F and G, is it the power series in Q or?
Yeah.
And then
So-
what do you mean by symplectic?
So we consider we work over this ring.
Mhm.
Yeah.
And symplectic mean what?
Symplectic means omega is a antisymmetric non-degenerate form on this infinite dimensional vector space
Okay.
over this ring.
Okay.
Yeah, you can ignore this. It is not essential. Yeah. So yeah, and element of Lx is a certain generating functions. So for example, JPN for some reason we keep tau with equal to or bigger than 2. Then we consider such function. This gives an element of Lx. This is called J function. Then by reversing the sign and multiply by minus z, it is the element of Lagrangian cone. No, I don't explain. Yeah. Yeah. Now. Easy. We can show you later. Yeah. Actually, finding a good point on Lagrangian cone, we can compute quantum cohomology. This means, in this case, we consider the partial differential equation satisfied by J function. Then we can see that yeah. Sorry. It is easy to see that J function satisfies this partial differential equation. And this corresponds to the relation. In general, it is difficult to write down explicitly the partial differential equation, but we can do this in principle. So if we know J function, then it is almost the same as we know quantum cohomology. given returning returning 10, they give an explicit formula of I function for toric varieties. I function means uh, some functions that gives the point on Lagrangian by this. I don't explain the detail, but J function is very special, very, sorry, this is very good point. There are no rigorous definition, but this is very good. And this, in general, this is not so good, but still we can compute Gromov invariant by using such function. So we can compute a J function. It means we can compute quantum cohomology of toric varieties. Same projective means projective of a fine variety. It corresponds to that there are enough functions over this variety. If you are not familiar with same projective, you can avoid semi. Same projective is broader than projective. Is there any question? Then I want to explain the construction of toric bundle. Let's consider this tuple. Here, the first one is a free abelian group. Of finite length. We impose some condition on omega. If we choose a good tuple, we can construct a toric variety. More precisely, we construct this toric variety by GIT quotient. So by taking the dual of D, we obtain we obtain subtori of torus of dimension n, and T naturally acts on Cn by diagonal action. So K also acts on Cn. Consider GIT quotient of Cn by K. Its stability condition is determined by this omega. So by definition, this is constructed as first, we remove some hyperplanes. Actually, these are coordinate hyperplanes. Sorry, coordinate subspaces. I'm taking usual quotient. For example, projective space can be described as D sends each basis to 1. Omega is D1. Sorry. This is 1. Consider this triple. Then corresponding toric variety is this GIT quotient, and its action is defined by the dual of this map. So just a diagonal action. So this is projective space. Okay. We do the relative version of this construction.
So in your discussion of the GIT quotient, so where is omega? So
Yeah.
you remove the coordinate subspaces. So is this S1 determined by omega or
Determined by omega.
determined by omega?
Omega, yes.
How is it determined by?
So for example, in this case, just a moment. So just first we consider okay, then let DI be the image of D of ice basis. So in general, okay, for the two case, rank 2 case, D1, DI is a point on L dual, so it's point on this. So we can visualize them like this. Okay. If omega is located in here, then consider a subset of 1, 2, 3, 4. These are order of the eyes. Okay. Such that, for example, now we consider 1, 4, 2, 3. These are if we consider the cone generated by D1 and D4, it doesn't contain omega. Okay. Maybe we should use another notation like this. I'm not sure. The cone, also cone generated by D2 and D3 doesn't contain omega. Okay, so in this case, we should remove coordinate subspace generated by first basis and fourth basis. And also remove coordinate subspace generated by these two bases. Does it make sense? Yeah, so for this case, now L is Z, so all the i's are just one. So like this. Omega is also located on them. So the biggest subset such that satisfy this condition is, in this case, just empty set. So in this case, we should remove coordinate subspace correspond to empty set. It is just point the origin. So we remove origin and then taking quotient. Okay. Is there any question? Yeah, I want to construct toric bundle by using this construction in a relative setting. So instead of vector space, I want to put here the vector bundle here. So let B is smooth projective variety and let L be a triple giving a toric variety, and B1, Bn, these are vector bundle over V. Then we can naturally obtain a toric bundle by imitating this quotient. And this bundle is endowed with fiber-wise torus action. Yeah, T acts on this bundle, but we take the quotient by case, so it reduces to T over K action. But to avoid heavy notation, I sometimes use T action. I define split torque bundle. This is the torque bundle obtained by line bundles. This case, actually we have a big torus action for each fiber. So localization formula works very well this case. So I first explain split case. So we set BI line bundles. And then torque bundle can be described as this. For each point of B, there is a torque bundle, torque variety XL. Here acts torus. Since it's big torus action, the fixed point fixed point set of this torus action on fiber is just a point, right? We can consider fixed points for each fiber, and by gathering them, we obtain fixed point set of torque bundle. These are all isomorphic to B. So the fixed point set is disjoint union of copy of the base space. A classical localization formula for equivariant cohomology says equivariant cohomology of total space is isomorphic to a direct sum of equivariant cohomology of total base space after taking a localization. This is a classical theorem. Sorry, it should take direct sum. This is a number of fixed points on the fiber. Brown proves that mirror theorem for space-toric bundle. So he gave an explicit formula of I function. In terms of a functional base space and L, and first term classes of line bundles. We now assume that vector bundles are all line bundles. This one, this isomorphism, it is just so there are n copies of B, so we have n inclusion of B into total space, right? And so just, okay, yeah, taking box. Okay. And first data corresponds to quantum homology base space. And this corresponds to fiber data. And the last one corresponds to gluing data. So this case, the first question is solved. Using these information, we can compute its quantum cohomology. I give a sketch of the proof. Remember that a function is defined as a function giving a point on the Lagrangian form. Here, this means that T equivariant version. Maybe you can imagine the T equivariant version. We should study point on this point, but using localization formula. It is established by we can get this Lagrangian form. Lagrangian form of a fixed point set. Explain. So it is known as so here this is direct sum of strengthening of copy of basis. So this is almost the same as 16 Lagrangian form of base space. It's known that using quantum Riemann method, we can relate a usual Lagrangian form with this one. By using this diagram, we can obtain the point of the form from point from LT. Can I explain the application of this method? Using this theorem, there is also a similar isomorphism for quantum mechanics. Now also just study convergence problem. Quantum homology by definition define the quantum homology is a formal deformation defined over formal ring. But in some case, it's convergent and we can consider deformation of a polynomial ring. For this case, this is the relation is 2n plus 1 minus 2 equals 0. And this is convergent, so we can consider deformation space over polynomial ring. Now, if the base space satisfies this condition, then quantum homology for that space also converges. A non-split case, we don't have good transaction. So we should need another strategy. Okay.
Yeah, so my previous question is actually occurred.
After this,
Yeah. But now it's
yeah, difficult to write down especially because we need to use mirror map. Yeah. So solve some bubble computation problem. Yeah, so it's almost impossible to write that. Yeah, but using a function, prove this isomorphism is not so hard. In my paper, the last part of my paper, I write the explicit computation for some special case. So, yeah, please. Finally, we consider a non-split case. The conjecture proposed by standard. And that K is a torus and K is also a torus where it is in K. And they are from A. And Y is a GIT quotient of X by A. And we and then and GIT is not the Lagrangian form. That here, but Y is variant column up. Theta proposed and the last theta just normal spiral. For the element of the Lagrangian form, we can define the map to when I say just a given health space. But they expect that this actually belongs to the Lagrangian form. This conjecture is motivated by symplectic theorem. The iron Anyway, in symplectic geometry, there is some Fourier transform phenomena for equivariant. And this is a quantum version of this phenomenon. First, the projective bundle case. So this case, we can interpret in some sense there is some Fourier transform when corollary. Quantum homology. That is of quantum homology. And by using this method, I proved that conjecture is true for all the I want to emphasize that in this case, we admit B to the non-split delta bundle. So there's no torus action there on QED. This case also we don't have a big torus action. So we can't use Berger localization formula here the same way as Graham case on split case. I use example for our function. This is the first bundle. With fiber isomorphic to product of two projective space. Let's add number to one by lambda. We have the first number for each projective space. Then here we shift the minus 3 and that's found in Armenian language. Lama specify T1 plus T1 then this is so we can complete this one down. Okay, first using our Bata local control. Then we can relate this Lagrange form with Lagrange form. So this concept. But unfortunately, this is there are not isomorphic to this case. In reality, have a product of projective space. So projective bundle. So by using that Fourier transform, how generalize.
Thank you very much. Are there any questions?
Yeah, I have one more. For your I number B X. Yeah, so at the end you replace number 1, number 2 by like URP2. So you don't have any error from here.
Yeah, I don't have any. Sorry, so then this is just 4 points. So you don't have transaction on. And in this case, there is but in general, there is some invariant one. So actually, in general case, we define Ti as invariant first answer. So here, now Ti has invariant first. So it remains Ti answer.
So do we know how to compute the quantum cohomology of analytically locally trivial projective bundle? So not Zariski locally, but yeah. Do you expect should be something because Classically, we have this Le theorem saying that yeah, the same decomposition holds for the but
For general projective space bundle, maybe it's called for general space bundle. But I'm not sure.
Yeah, namely, which is a projective bundle, but which is not the projectivization of some vector bundle. Yeah. Okay. So are there more questions? If there is no more question, then let's thank Yuki again for his nice talk. So thank you very much.